All right, last time we talked about momentum, and now we're going to use the idea of conservation of momentum to help us understand inelastic collisions. And we're also going to, in the process, learn about a thing called the center of mass and how to transform into the center of mass reference frame. So here we go. Now, collisions. Collisions are an important thing to know how to work with, how to solve problems with. For example, collisions show up all the time. Tackling someone in football, two swords hitting each other, a baseball hitting a bat, two molecules coming together to undergo a chemical reaction in a vapor, someone catching a ball, a comet flung around the sun, right? That's a collision. Even if the comet doesn't hit the sun, they interact. And as a result, when they're a long ways from each other, they have certain velocities. And then after they've interacted and they're a long ways away from each other again, they have different velocities. That's something we would call a collision in physics. Or say like a neutron being absorbed by a nucleus. So the aspect of collisions that we're going to try and understand in this class is basically I have initial velocities for two objects. How do I find the final velocities of the two objects after they have collided? Now, in a standard collision problem, you've got several parameters. You need to know the mass of each particle. There's an initial velocity of each particle and a final velocity of each particle. So there's all these different parameters that are related to each other, and usually what we're trying to do is say we're given some of them and we're trying to find the others. In particular, for a problem with two particles, there are two masses, two initial velocities, which are probably vectors, possibly vectors, and then there's two final velocities, which could be vectors as well. So if, for example, we're given the initial velocities and the masses of the objects, and we're trying to find the final velocities, well, there's two final velocities to find. So that means we're going to need two equations to find our two unknowns. Where do we get our equations? Well, conservation of momentum will be one of them. Where do we get the other one? Well, it depends on what kind of collision we're dealing with. So there's two different types of collisions. There's what we call an elastic collision. In an elastic collision, energy is conserved. It's like two billiard balls hitting each other, right? That they hit each other and kinetic energy is conserved. The kinetic energy doesn't go somewhere else. Now, in real life, except in quantum mechanics, you never really have truly elastic collisions, right? My two pool balls hit together. The balls vibrate just a little bit. Now, not very much. You don't see them vibrating because not much energy goes into the vibrating. But you know what? You can imagine after a ball gets whacked, it's going to vibrate a little. You hear sound. When the balls hit, they click together. Here they go. Here they come. And click. Did you hear that? So some energy was lost due to that sound. So in real life, we generally don't deal with truly elastic collisions, but oftentimes collisions are close enough to being elastic that we just pretend like they are and we solve our problems that way. So if we're dealing with an elastic collision, the second equation is basically conservation of kinetic energy. Now, we're not going to deal with elastic collisions in this video. We'll talk about those in the next video. The other type of collision is an inelastic collision. That's one where kinetic energy is not conserved. Surprise, right? Elastic is conserved, inelastic it's not. So an elastic collision is something like where I have two balls that are slightly squishy, and so when they run into each other, some of that kinetic energy is transferred into vibrational energy of the balls. Or it could be, sound, like we talked about, with our two pool balls sitting together. Or it could be something like, two cars collide and energy is taken up by bending metal. It takes energy to do the work to, bend the metal. And so that would be an inelastic collision. Now, it turns out that inelastic collisions can also, in addition to reducing the kinetic energy, it's possible for it to have an inelastic collision where the final energy is actually greater than the initial energy. Like if, for example, one of my balls was spring-loaded, so as soon as they hit, the spring gives off its spring potential energy to make the balls fly apart faster. Or maybe one of the balls has an explosive on it, and they hit, and it goes bang, and they fly apart. So it's possible to take some other form of energy and in the collision convert it into kinetic energy. All right, I could have two molecules in excited states collide and some of that energy gets converted to kinetic energy. That's less common than having collisions where you come out with less kinetic energy, but it is a possibility. But in general, inelastic collisions are more difficult to deal with because we don't have that second equation, energy final equals energy initial, right? We don't have conservation of kinetic energy. We do have conservation of momentum. That gives us one equation. Where do we get the second equation? Well, that's tricky, but there is a special case of inelastic collision that turns out not to be too difficult to solve, and that's what we call a completely inelastic collision. A completely inelastic collision is the inelastic collision which reduces the kinetic energy by the maximum possible. All right, so we have this collision, and the final kinetic energy is lower than the initial kinetic energy by the most possible. And it turns out the way to get the maximum reduction in kinetic energy is to have the colliding objects come together and then stick together, move at the same final velocity. So, for example, if I put some chewing gum on one of my balls, so they stick together, when they collide, they stick together, and that is the condition where you have the lowest possible kinetic energy after the collision. Now, in the case of a completely inelastic collision, then, we know that the two objects are traveling at the same velocity after the collision, and that's our second equation that will help us solve problems. So, for a completely inelastic collision, I have conservation of momentum. I always have conservation of momentum. But in the case of a completely inelastic collision, I also have an equation that says the final velocity of object 1 is equal to the final velocity of object 2. And we'll just simplify that and call them both v final. So my equation for conservation of momentum is just mass 1 v1 initial plus mass 2 v2 initial is equal to mass 1 v1 final plus mass 2 v2 final. And then applying the second condition, the second equation, that the two final velocities are the same, I can replace v1 final and v2 final with just v final. Then I can factor out the v final and then divide both sides by the sum of the two masses, and I get my solution. All right? So in a completely inelastic collision, the math actually is not that bad. So here's an example. An astronaut with a mass of 50 kilograms is floating motionless outside of the International Space Station. Another astronaut pushes a 33.3 kilogram Einsteinian hyper-electrolytic passive recombination dielectric nuclear warp decomposition cell toward her with a velocity of 1.33 meters per second in the x direction plus 0.25 meters per second in the y direction. What will her velocity be after catching the decomposition cell? Well, solve this the vector way. The initial momentum equals the final momentum, and the two final velocities are the same. So if our initial momentum equals the final momentum, that means the mass of the astronaut plus the initial velocity of the astronaut plus the mass of the cell times the initial velocity of the cell. That has to equal the mass of the astronaut times her final velocity plus the mass of the cell times its final velocity. Well, in this case, the astronaut is initially not moving, so that first term goes to 0, and that equation gets a little simpler. And then we use our second equation, and we say, the final velocity of the astronaut and the final velocity of the cell are both just v final. They're the same thing. So we plug that in, factor out the mass, divide by the sum of the masses, and there's our answer. We could also solve this using components. So here we wrote momentum and velocity as vectors. But if momentum is conserved, that means that each of the individual components of momentum have to be conserved. If P initial equals P final, that means the x component of the initial momentum has to equal the y component of has to equal the x component of the final, and the y component of the initial momentum has to equal the y component of the final momentum. So we can solve this in terms of components. We can just think about the x component. So the initial x component momentum equals the final x component of momentum. And then, once again, if their two final velocities are the same, the x component of their final velocities have to be the same. So our momentum equation says mass of the astronaut, the x component of the astronaut's initial velocity, plus the mass of the cell, plus the x component of the cell's initial velocity, must equal the mass of the astronaut times the astronaut's final velocity x component plus the mass of the cell times the x component of the cell's final velocity. And of course, the initial velocity of the astronaut is 0, so that means the initial x component of the velocity is 0. That first term goes away. Then we replace the x components of the final velocities of the astronaut and the cell with just v final x because they are the same. Factor out the masses, divide, and then we have the final x component of the velocity. We can do a similar thing to find the final y component of her velocity. And then we can plug in the numbers and we find her x and y components of her final velocity. But why? Why is sticking together the type of collision that minimizes kinetic energy? Why is this true? Well, to figure that out, it helps to understand center of mass and the center of mass reference frame. We need to understand what the center of mass of something is. And we'll need to know about center of mass and center mass reference frame for other things as well. So this is a good time to learn about the center of mass. The center of mass of an object or a group of objects is simply the sum of the masses of each object times the position of each object divided by the sum of the masses. It's basically a mass-weighted average position. So for example, if I have two equal masses, one at x equals -1 and one at x equals 3, the center of mass is just their mass-weighted average position. It's the point directly between them, right? And we can use our formula to count that, to calculate that. So the center of mass is just the mass of object 1 times its position, -1, plus the mass of object 2, 1 kilogram, times its position, 3 meters, divided by the sum of the masses, 1 kilogram plus 1 kilogram. Plugging that in, we find then that the center of mass is 1 meter, which is exactly halfway between -1 and 3 meters. But now, one of the masses was smaller than the other. What if this first mass was smaller? Well, then, because this is a mass-weighted average, the center of mass is going to move closer to the larger mass. And once again, we can calculate this. The center of mass location is going to be the mass of the first particle times its position, plus the mass of the second particle times its position, divided by the sum of the masses. And we plug that all in, and we get 1.67 meters. So it's a little closer to the more massive ball. If the first ball was more massive, then it's going to move the center of mass closer to it. And once again, we can plug in the numbers. 1 kilogram times -1 meters plus the mass of the second ball times its position divided by the sum of the masses, and that is the location of the center of mass. Well, what if our masses have x and y components? Once again, the center of mass will still just be somewhere between them. It's the mass-weighted average position. So the location of the center mass is going to be the mass of the first particle times its location, which is -1 meter in the x direction, plus 2 meters in the y direction. And then we add that to the mass of the second particle times its location, which is 3 meters in the x direction, plus 2 meters in the y direction. Divide that by the sum of the masses, and we get the location in the center of the mass. And you can do this with more than 2 particles, 3 particles, a whole bunch of particles. All right, you just add the mass times position, the vector position, for each particle, and then divide that by the total mass summed up for all of the different objects. Now here's a little cool thing that I'm going to show you that can help you when you work homework problems. So the location of the center of mass of a bunch of particles is just the sum of their masses times their positions divided by the sum of their masses. Well, let's break these sums up into 2 pieces. Let's break them up into a sum from n equals 1 to m, and then another sum from n equals m plus 1 to n. So it's the same masses, but we're dividing them into 2 groups. All right? But now, watch what happens. I'm going to multiply this first sum in the numerator by this same sum I have in the denominator. All right? Notice that this sum right here is just the sum of all of the masses in the first group. It's just the total mass of the first group. And this one right here is the sum of the masses in the second group. All right? And then I'm multiplying here by the total mass in the first group divided by the total mass in the first group. And then I'm going to multiply this other sum by the total mass in the second group divided by the total mass in the second group, right? We're just multiplying by 1. All right? Well, notice that this divided by this, that's the mass times distance, sum of the mass times distance divided by the sum of the mass. That is just the center of mass of the first group of objects times the mass of the first group of objects, and this is the center of mass of the second group of objects times the mass of the second group of objects. So this is basically just mass of group 1 times the center of mass of group 1 plus mass of group 2 times the center of mass of group 2 over the sums of mass of group 1 and mass of group 2. Well, wait a minute, that's just like finding the center of mass of two particles, right? Right, if I had two particles, this, particle 1 and particle 2 that have position 1 and position 2, that's exactly how I would calculate the center of mass. So what does that tell me? It tells me if I have two groups of particles, and I know their center of masses, and I know their total masses, I can find the center of mass of the combined system just by pretending like I had a point particle with the mass of group 1 at the center of mass of group 1, and another point particle with the mass of group 2 at the center of mass of group 2. So we can break our center of mass calculations up into pieces. Now, what if you don't have point particles? What if you have things with continuous mass? Well, then you can find the center of mass by, instead of summing, you integrate. You integrate distance of a little infinitesimal mass and integrate that over all of the little infinitesimal pieces of mass, right? You break your object into little pieces and add all of those up and then divide that by the integral of all the little masses. Well, of course, a little piece of mass is density times a little volume. All right, so we can place dm with density times d volume. And of course, the bottom integral is just the total mass of the system. So this is how you would find the center of mass for something that was like continuous rather than a bunch of infinitesimal point masses with finite masses, right? Okay, so now we know about the center of mass position. What's the velocity of how does the velocity of the center of mass change as particles move around? Well, this is our definition of the center of mass. To find the velocity of the center of mass, we just take the time derivative of that. And of course, the masses of each particle are constant. So we can bring the derivative in and say, oh, this is just the sum of each masses times velocity rather than radius, right? We just take the derivative of position to get velocity. Well, mass times velocity, that's momentum. So the velocity of the center of mass is just the sum of the momentums of all of the particles divided by the sum of the masses. Well, guess what? Momentum is conserved. If I have a bunch of objects and they're only interacting with each other and nothing else, then the momentum of all of my objects is going to stay the same, which means that the velocity of the center of mass will be constant if there's no forces acting on these particles outside the particles. So the particles can interact with each other. The objects can, I can have objects on springs, objects interacting with gravity or electromagnetic forces. I can have objects bumping into each other. But if the only interactions are within this group of objects, that means the center of mass of those objects will be constant with time. All right. Now, so the velocity of the center of mass is just the total momentum of my objects divided by the total mass of my objects. If I rearrange things, that tells me that the total momentum of my system is just the total mass of my system times the velocity of the center of mass of the system. Cool. Now, what is the acceleration of the center of mass? Well, I'll take the derivative of the velocity, and that just gives me the derivative of the total momentum divided by the total mass. If I multiply both sides by the total mass, right, it's a constant, it comes out of the derivative, I find that the total mass times the acceleration of the center of mass is equal to the time derivative of the total momentum. But of course, d momentum dt is just the force. So the total mass times the acceleration of the center of mass is equal to the net force on the system. And it turns out the net force on the system are just the external forces on the system, right? Because if I have objects inside the system, there's going to be equal and opposite forces, right? If particle 1 pushes on particle 2 pushes back. And so when we look at the net force, that cancels out. So the net force for all of the stuff on our system is just then going to be the sum of the external forces on the system. So for example, imagine I take two masses, they're different masses, and they're on a spring, and I throw them into the air. They're going to do all kinds of funky things. But the center of mass of this object is just going to follow the trajectory that you would get for any solid object with the same external forces on it. All right, so if I put a red dot on here, that shows the center of mass of these two things as a function of time, notice that the center of mass of my system just follows a parabolic trajectory. So I throw my two masses on a spring into the air. They do funky things together, but the center of mass just follows Newton's second law, F equals ma. Similarly, imagine I had a rocket out in space that was just coasting. We would expect that rocket, since there are no forces acting on it, to just move at a constant velocity. Well, what if instead we saw the rocket doing this? We'd be like, oh, rockets can't just wiggle like that without forces on them, so there must be forces on it. And then we investigate and find out there are no forces. And then we say, now I understand. There are no forces. That means that the center of mass is moving at a constant velocity, but maybe there's some big giant robot running around and jumping up and down inside the rocket, such that the center of mass of the rocket changes relative to the sides of the rocket walls. But as that such that as the center of mass moves at a constant velocity, the outside of the rocket is jiggling around in order to keep the center of mass moving at a constant velocity. All right, now we're going to talk about changing inertial reference frames. So it turns out the laws of physics are the same in all inertial reference frames. What is an inertial reference frame? It's one that's not accelerating. It's one in which something that has no forces acting on it will not accelerate. Now, remember, the Earth is not an inertial reference frame, right? We have things like the Coriolis force that we use to make up for the fact that the Earth is rotating, right? That we do our experiment, but the Earth rotates underneath it. But let's not deal with accelerating reference frames like the Earth rotating. We're going to deal just with inertial reference frames, and the laws of physics are the same in all inertial reference frames. So that means if I go from one reference frame to another, that means going to a frame that's moving at a constant velocity relative to another frame. So imagine I'm doing some measurements and I want to transform into how would these measurements look like to someone driving by on a bicycle at a constant velocity vref? Well, all I have to do is I have to take all of my velocities and subtract the velocity of that reference frame, and that will give me those velocities in that reference frame, right? If I see a ball flying by at 10 miles an hour to the east, and someone rides on their bike at 5 miles an hour to the east, right, they're going to see the ball in their reference frame moving at just 5, right? The velocity in my frame minus the velocity of their frame relative to my frame, all right? Now, so it turns out if I go in from one inertial reference frame to the other, the momentum and the kinetic energy will be different in the different reference frames, right? If I have a ball that's sitting still in my reference frame, if someone rides by going east at 5 miles an hour, and their reference frame, the ball is moving west at 5 miles per hour. So in my reference frame, the ball has no kinetic energy and no momentum, but in the reference frame of the person on the bike, the ball is moving, therefore it does have kinetic energy, and it has momentum in the backwards direction. All right? So they will be in different reference frames. Systems will have different momentum and kinetic energy. However, momentum is conserved in all inertial reference frames, and if kinetic energy is conserved in one inertial reference frame, it will be conserved in all others. Okay? So now let's see what happens when I transform to the center of mass frame. So the center of mass frame is the frame that moves with the center of mass. It moves at the velocity of the center of mass. And it turns out the center of mass frame is the reference frame in which momentum is 0, right? We already showed that. We already proved that in the center of mass frame, our system has no momentum, no initial momentum, and no final momentum because momentum is conserved. So the velocity we said of the center of mass frame is the sum of the momentums of the particles divided by the sum of the masses of the particles. All right? Oh, I haven't proved that the momentum is 0 in the center of mass frame. I'm getting ahead of myself. We're going to do that now. All right, so if I have a bunch of particles with different masses and velocities, right, I can find the velocity of the center of mass because we found that earlier, right, that it's just the sum of the momentums divided by the sum of the masses. Well, now let's transform into the center of mass frame. What is the momentum in the center of mass frame? Well, the momentum is just mass times velocity, but now the velocities of my particle in the center of mass frames are just the velocities of the particles in the original frame minus the velocity of the center mass frame, right? That's how we transform velocities. Well, I can take this sum and separate it into two pieces. All right, the first piece is just mass times the velocities, so that just gives me the momentum in the original frame. And then I have mass times velocity of center of mass, so we subtract that sum. Well, center of mass is the same, it's just a constant, right? It doesn't have anything to do with any particular object, it's the sum of all the objects, so I can pull that out of my sum. All right, but now I know the velocity of the center of mass of my system is this thing right here, so I'll plug that in. And now the sum of the masses cancel out, and I'm just left with the sum of momentums minus sum of momentums. And I then have just proved that the momentum in the center of mass frame is zero, right? So conservation of momentum, that means the initial momentum of my system is zero and the final momentum of my system is zero. Okay, so now let's look at our inelastic collision. All right, this is the simulation I showed before, but now let's put a grid behind them so we can see how they're moving relative, to the floor or whatever, to the wall. Now let's move into the center of mass frame. In the center of mass frame, we're going to be moving with respect to the grid. All right, we're going to be moving at the velocity of the center of mass of the system. Here we come. Boom. That's what happens in the center of mass frame. All right, so now let's look at our completely inelastic collision where they stuck together. Boom. Now, here they come. Squish. Now let's go into the center of mass frame. Boink. They just stick together. In the center of mass frame, the initial momentum is zero and the final momentum is zero. So initially, the two objects are moving in opposite directions such that their momentums cancel out. In the end, when they stick together, there's no momentum because they're not moving. Neither of them is moving in the center of mass frame. Well, nothing moving is the lowest kinetic energy you can get. So clearly, sticking together, moving at the same final velocity, is the lowest kinetic energy possibility that conserves momentum in the center of mass frame. But is minimizing the kinetic energy in the center of mass frame the same as minimizing it in some other frame? Well, let's say the final kinetic energy in some other frame is, it's just 1/2 m1 v1 squared plus 1/2 m2 v2 squared. Well, let's compare that to the kinetic energy in the center of mass frame. To go to the center of mass frame, right, we just take each of our velocities and subtract the center of mass. And then we get the kinetic energy in the center of mass frame is 1/2 m1 times the velocity of object 1 in the center of mass frame squared, plus 1/2 m2 times the velocity of object 2 in the center of mass frame. There should be a 2 there. I apologize. All right. But let's find now the kinetic energy in the other frame, not the center of mass frame, but let's write it in terms of velocities in the center of mass frame, right? So if velocity 1 center of mass is velocity 1 minus the velocity of the center of mass, velocity 1 is going to be velocity 1 in the center of mass frame plus the center of mass, velocity of the center of mass, all right? So here's the kinetic energy in the original frame, and we want to see how that compares with the kinetic energy in the center of mass frame. Well, here it is. Let's expand. Let's do the squares. Let's expand the parentheses. And when I expand this one right here, I get this. I get, V1 squared, V1 center mass times V center of mass, and then I have V center mass squared, right? And then I do the same thing with this other term here. Notice that these two terms together add together to give me just the kinetic energy in the center of mass frame, right? And these two here add together to give this, and this has nothing to do with velocity 1 or velocity 2. So whatever we decide the final velocities of our particles should be, that term doesn't change. All right, so the only term we have to play with right here to, what should the final velocity be in order to minimize the kinetic energy in not the center of mass frame, it's this one right here. But notice this is just the momentum of particle 1 in the center of mass frame. This is the momentum of particle 2 in the center of mass frame. So this is just the total momentum in the center of mass frame, which we know is zero. We proved that the final kinetic energy, the final momentum in the center of mass frame is zero. So that means this is zero. This doesn't change if we tweak the velocities, and this is the kinetic energy in the center of mass frame. So if we minimize the kinetic energy in the center of mass frame, we have minimized the kinetic energy in any frame. Therefore, the collision that minimizes kinetic energy while conserving momentum in any reference frame is the one where the objects end up moving together at the same velocity after the collision. All right, that's all I've got for you today. I hope you learned a lot from this. I hope that these animations that I made were instructional and helped you understand what was going on, because my goodness, they took many hours to create. But if they are not helpful and useful, at least I had fun making them. We'll see you next time.